This screencast covers slides 64 through 72 in the version of the Thermo PowerPoint dated February 25, 2016. The topic is analysis of binding data and design of binding experiments, part 2, total ligand relationships. So the key point here is going to be, there's sort of two main takeaway messages from this. They're sort of unified by the same, what I call mathematical trick to think about the relationship between free ligand binding isotherms and total ligand binding isotherms. So at the end of this, the goal is to understand in a qualitative way, using this, again, relatively simple mathematical trick, what the relationship is between free and total ligand in the course of a binding experiment. And the reason that's important is both because you need to do that to properly analyze binding data, but also once you understand that, that's the best way to think about the design of binding experiments. So this simple mathematical trick connects to both the interpretation and the design of binding experiments. It's really the single most important thing in terms of designing binding experiments. What we'll see is that the relationship, the ratio of the total receptor concentration to the dissociation constant is a key determinant of the qualitative behavior of the experiment and therefore the design of the experiment. So let's get going on this. So this slide you've seen before. It illustrates a model, sort of in vitro binding experiment. In this, these are simulated data, but realistically representative of real data. Progressively small amounts of a ligand are added to some fixed amount of receptor, presumably in a test tube. There are many in vivo experiments in cells that are designed and interpreted in a way that assumes something like this is going on in the cell. But the simplest and most straightforward incarnation of this would be having a purified protein in a test tube where you progressively add more and more ligand. Now, so as you do this, you know the total amount of ligand that you've put in the tube. And in this case, we're observing some arbitrary signal, but that is assumed to be linearly proportional to the amount of complex receptor ligand complex formation. And so then that signal is plotted as a function of total ligand. And again, the assumption is the movement of the increase in the signal along the vertical axis here, or the ordinate. It's assumed that that's linearly proportional to the concentration of the complex. So we've been through all this before. And one key point, however, is that when we do this experiment, sort of the natural coordinate system that we end up with, the simplest thing to plot is signal as a function of total ligand. But the mathematics that we've developed so far to treat equilibrium binding is all based on free ligand, right? So the simple mathematical equations that we've had to this point are based on free ligand, but this is based on total ligand, and so we need different methods to analyze the data. So that's the central topic here, and understanding how to do that leads us directly to understanding the key parameter in designing binding experiments, which is the ratio of the dissociation constant to the total receptor concentration. So I'm going to come back to that again and again, and effectively try to beat it into your head in the course of the screencast. So let's move on to the next slide then. And again, the main thing we're going to focus on is what kind of method we can use to look at data in total ligand binding curves plotted as a function of total ligand. Before we move on, I'll just make one comment on free ligand. There are some experiments where free ligand is measured or known. Two of them, I'm going to explain them now. There's something called equilibrium dialysis. In that experiment, free ligand concentration is directly measured. There's another thing called a Hummel dryer, which effectively takes place in sort of a free ligand space. So there are ways to directly assess free ligand, but this is by far the more common way of doing an experiment, is adding total ligand or measuring total ligand In a test tube, you would typically be adding a known amount of total ligand. In a cell, you'd probably be actually measuring total ligand and correlating that with some other parameter. Free ligand plots are useful for many reasons. There are also experiments where you directly measure free ligand. But this plot, this kind of experiment where you know total ligand, is more common. And then, as I said earlier, this is also directly connected to experimental design. So let's get going on the substance of this. Okay, so we've seen this before. This is, of course, up here is the fundamental mathematical equation describing the kinetic condition to achieve an equilibrium. The stoichiometry variable here, we're still going to sort of ignore it for now. At the end of this screencast, we're going to have to begin to dig into it a little bit more deeply, but I'm going to mostly defer consideration of this to a different screencast. Stoichiometry has a somewhat complicated interaction with cooperativity, right? So this S here is the stoichiometry, and here is the so-called kinetic cooperativity. They do have a somewhat complicated relationship, but for the moment we're going to just completely put that out of mind, and then we'll cycle back later to stoichiometry. So for the moment we're just going to sort of consider the stoichiometry to be combined with the receptor, and so we're going to assume that SRF is the actual concentration of free receptor, and SRLN is the actual concentration of receptor that has N ligands cooperatively bound to it. So let's go forward with that. So if we want to now go from begin to develop mathematical tools and conceptual understanding of what happens in binding experiments when we're looking at total ligand, of course we have to mathematically consider how free ligand is equal to total ligand. So this is fairly straightforward. Free ligand is, of course, total ligand minus bound ligand. The only slightly complicated thing here is the role of the cooperativity. For the moment, we're just going to consider this in a very simple, somewhat simplified way, but a way that's sort of, I think, easy to understand. The model here is that N ligands bind cooperatively, apparently simultaneously, to a receptor. So let's say N is 2. If N is 2, if we have 1 micromolar of their bound receptor complex, each receptor has 2 ligand molecules bound to it. That means we have 2 micromolar of ligand bound to the complex, right? So if there are N molecules of ligand bound cooperatively to the receptor, we have to take the receptor complex concentration and multiply by N to get the bound ligand concentration. So then the free ligand would be the total minus the bound. The bound is the number of ligands bound per receptor molecule times the concentration of bound receptors. So hopefully that's pretty straightforward. We rearrange this. Is trivial rearrangement, then we get the total receptor is equal to, the total ligand is equal to the free ligand, and N times the concentration of bound receptor, which then gives us the concentration of bound ligand. So what we get here is the total ligand is simply given by again, total ligand is free ligand plus bound ligand. So simple enough. Now, I am having a trouble at the moment actually being able to write anything on this screen. It should happen in a straightforward way. It does not. There's some kind of bug in my screencasting hardware/software setup, and so for today, for this screencast, we're just going to have to settle at me pointing at things. I apologize for that. Okay. So, right. So in some sense, this simple equation, right, totally simple, total ligand is free ligand and bound ligand. In some sense, this simple equation solves the entire problem. The entire thing we're trying to understand now is how we go from a plot in free ligand, of the kind that we've been, developed the math for before, how we go from this free ligand plot to the total ligand plot. Well, a total ligand is just free ligand plus bound ligand. This is totally simple arithmetic, and really, in a fundamental level, this is all we need to know to deal with this. But how exactly this simple equation applies in this situation is a little bit tricky, and so we're going to go through that step by step. So first, let's consider one specific point. Let's consider the point of 50% saturation, right? We've seen before that the free ligand concentration at 50% saturation is always Kd. As long as we define the binding constant in this manner, as long as we see kd to the n, is equal to the ratio of the reverse and forward rate constants and is at equilibrium, will be the ratio of the product of the free receptor times the free ligand to the n over the concentration of the bound receptor. As long as we describe that fundamental concentration ratio at equilibrium as kd to the n, once we make that mathematical definition, the 50% saturation point for any receptor is when the free ligand concentration is equal to kd. So irrespective of cooperativity, having made this definition, irrespective of cooperativity, we get 50% saturation when free ligand is equal to kd. These are simulated data with a kd of 5 micromolar. We always have 50% saturation and when the free ligand is 5 micromolar. As we get different levels of cooperativity, the shape of the curve changes, but they always intersect at this point. So this is, as we talked about earlier, sort of a universal reference point in binding experiments. Previously, we had talked about that reference point relative to free ligand concentration. We now want to understand what goes on, where that point is when we look at total ligand. Well, this is quite simple. The total ligand at 50% saturation will be the free ligand at 50% saturation plus the bound ligand at 50% saturation. At 50% saturation, of course, half of the receptor is bound. So if we take SRT over 2, the actual concentration of bound receptor, and we multiply by that by n, the number of ligand molecules bound to each receptor molecule, this is quite straightforward. The total ligand is equal to the free at 50% saturation plus the bound, which at 50% saturation is half of the total times the number of ligands bound per receptor molecule. But we also know from what we just discussed that at 50% saturation, the free ligand concentration is also something we know. It's going to be kd. Right? And so, sorry, the animation there probably should have gone in the other order. But, right, the free ligand 50% saturation is always kd, so that's straightforward at equilibrium. The bound concentration is RT over 2 times S times N. For the moment, let's just consider this to be SRT times N, SRT over 2 being the concentration of bound receptor, and then N being the number of ligand molecules per receptor molecule. So we know the total ligand in a very straightforward arithmetic way. In general, it's the free plus the bound. At 50% saturation, it is specifically the free, which is kd at 50% saturation, plus N times SRT over 2. So what this means is that going from free ligand to total ligand, we just have to sort of arithmetically move along the ligand concentration axis, right? So if this is a free ligand plot, if we now want to go down to a total ligand plot, total ligand free plus bound, and so if we, what the data are, the simulated data here are all, now these are all n equal 1 data, so we're still using a receptor with a dissociation constant of 5 micromolar. So the black curve here is essentially showing the free ligand relationship. I'll come back to that in a moment. And as you do the binding experiment with more and more receptor, well, the free ligand at 50% saturation, right? The free ligand at 50% saturation is always the kd, right? The free ligand at 50% saturation is always this point. But as you have more and more receptor, of course, half of the total number of possible binding sites at 50% saturation, half of all the possible binding sites are occupied. So as the amount of receptor goes up, you have a greater and greater displacement between total ligand and free ligand. And so hopefully that's very straightforward. And really, in some sense, this is all there is to thinking about, at least to understanding, the relationship between the total ligand binding curve and the free ligand binding curve. Right? Whatever the free ligand binding curve is, because the free ligand, right, the relationship between free ligand and fractional saturation is always the same. The only thing we have to worry about then is the amount of receptor. And as there's more and more receptor, you get a bigger and bigger amount of bound. And so the total being the sum of the free and the bound, as you get more and more receptor, you have a higher amount of total ligand. So at some level, that's really all we need to understand, and it's very straightforward. The 50% saturation point is very convenient because we know the free ligand is equal to Kd. So that's a very simple reference point, what I've called before the universal reference point. And then at 50% saturation, we also know the bound is going to be half of the total receptor times the number of ligand molecules bound per receptor molecule. And so as we get more and more receptor, we get a increasing, linearly proportional displacement of the 50% saturation point on the total ligand axis. So if you stop and think about that, if you need to pause the screencast, hopefully that all makes sense. So now this next step is to think about, sort of qualitatively how this varies depending on the amount of receptor we have. And so what's simulated here are fractional saturation relationships for a receptor with a Kd of 5 micromolar for different experiments connected with different amounts of receptor. Here it says RT equals 0.1, RT is 0.1 micromolar for the black, then 5, then 10, then 25 micromolar. Yes, I'm sorry, there is a typo here. There are a bunch of typos here. I'm sorry about that, but because you guys really need to sort of see this and move on, I'm going to go ahead. I'm going to fix this up. I apologize for that. I can see by looking at this that there's some typos here. But for today, we're going to move on. And maybe by the end of the screencast, you'll understand quite clearly how I can just look at this very, very simply and understand that there's a typo here. Well, sorry for the confusion, but let's move forward. So quantitatively, there is a problem with these numbers, but qualitatively, the principle is entirely correct. As we get to more, as we put in more and more receptor, the free ligand at 50% saturation, right, is always Kd. As we put in more and more receptor, of course, there's more total ligand bound at 50% saturation because the bound population increases. So hopefully that's quite straightforward. Just to think again about sort of the magnitude of this effect. So let's just start here with RT equals 0.1. So if RT equals 0.1, and for the moment we're assuming this is n equals 1, and we're assuming n equals 1. So basically NSRT is going to be 1. I'm sorry, NSRT in this case is 0.1. That means at 50% saturation, half of that total number of binding sites are occupied, and so NSRT over 2 is 0.05. So on this scale, right, this little unit is 1. 0.05 would be 1/20th of that. It's sort of the amount of total ligand bound at 50% saturation in an experiment done with 0.1 micromolar receptor would be basically about the thickness of that little tick. Right? So the free ligand relationship is always the same. If we have only a very small amount of receptor in the experiment, when we add in when we take the free and add the total, that addition is just a tiny shift. So there's a tiny shift between the free ligand and the total ligand. Right here it would be about 1 tick width. Out here it would be closer to 2 tick widths. It's still almost imperceptible. And if you put noise in the data, it probably would be entirely imperceptible. So this is a key point. When the experiment is conducted with a very low receptor concentration, there is just a very small displacement between the free, there's a very small difference between free ligand and total ligand, right? If free ligand at 50% saturation is 5 micromolar and NSRT is something much smaller than 5 micromolar, in this case, it's 1/100th of that, right? There's an imperceptible difference. Under this condition, the free ligand curve almost matches the total ligand curve. We'll come back to that several times in treating the next few slides. So if you don't follow that yet, hold tight and hopefully it will become clear. Now, as we have more and more ligand, there's more and more of a displacement. How can we interpret that? Well, we can still use this equation to interpret that point. the total ligand concentration at 50% saturation will be the KD plus half of the total receptor concentration times N, right? Now, so one important point here is that the total ligand concentration at 50% saturation is not equal to KD, except under special circumstances. The total receptor will equal KD under the special circumstance where there's a minimal amount of receptor. When you have a significant amount of receptor, you have to add in the bound, and then as the amount of receptor becomes higher and higher, that displacement, that amount of bound becomes, that amount of bound becomes larger and larger and larger, and there's a bigger and bigger difference, and eventually there is, a very big difference between L total and half saturation and KD, right? So this point is routinely ignored in the literature, and that means when people, can see that as you use more and more receptor, there's a bigger and bigger difference between the total ligand and the free ligand at 50% saturation. And as you use more and more receptor, if you ignore that point, you make grosser and grosser errors. And we'll see shortly that those errors can actually be many orders of magnitude. And so we're going to try to get to the point where you understand that clearly. Okay, so, but now if we look at this, we can already see a very simple way to correct for the fact that the total ligand, we can see a very simple way to analyze data that are plotted based on total ligand and understand what the free ligand is, right? And so that approach is given by this simple equation, effectively. If we take the total ligand at 50% saturation, will be the free, which is KD from the bound. If we take the total and subtract out the bound, we're going to get the KD, right? If we take the total ligand and subtract out that amount of bound ligand, we will get the KD. So this leads to an idea that I call graphical correction, which is explained on the next slide. We're going to take the total ligand at 50% saturation, subtract out the bound, and that will give us the free. So this is shown explicitly on the next slide, right? So just to repeat what was just said, the total ligand at 50% saturation is equal to KD, the free ligand, plus NSRT over 2, the bound ligand. And so that means the KD, right, this is what I said as I was just a few moments ago, the KD at 50% saturation, the KD will equal the total ligand at 50% saturation minus the bound ligand at 50% saturation. So if we have a knowledge or even an estimate of the total ligand concentration in the experiment, we can divide that by 2 because at 50% saturation, half of the receptor is bound. And so we take basically NSRT over 2, our estimate of the bound, subtract it from the total, and we get the KD. And this leads to this idea of graphical correction. This is the first thing you want to do whenever you look at the binding curve. You want to do a graphical correction. So if you get to the exam and you see a binding curve and your immediate reflex is to do the graphical correction, you're in great shape for the exam, right? So here's an example where SRT is 5 micromolar. In this case, the KD that was used to simulate these data are 2 micromolar. But let's look at the 50% saturation curve right now. So we're looking, let's be very clear, we're looking at a plot of fractional saturation versus total ligand. We're going to the 50% point in fractional saturation. In this case, to keep things a bit clearer, we're just using fractional saturation values. If we had actual data, we could still find this point, right? We could just look at where the binding, we could look at where the signal starts and where the signal saturates and just roughly go to the 50% point in signal saturation, right? That's going to give us roughly the 50% saturation point. To keep the analysis just a little bit more clean, in this case, we're plotting directly fractional saturation. So we go to the 50% fractional saturation point on this total ligand binding curve. So we find the total ligand at 50% saturation. We subtract out from that. In this case, n is equal to 1, right? So NSRT over 2 is just half of the total receptor concentration. At 50% saturation, half of the receptor is bound. We take the receptor concentration bound by 2, divide by 2. We have 1 ligand bound for receptor molecule in this case. So we subtract out NSRT over 2. And what do we get? Well, we get 2 micromolar, which is KD, right? the bottom line is at 50% saturation, the free ligand is always the KD. That's the universal reference point. If we have a curve in total ligand, all we need to do is subtract out the bound at 50% saturation, and we always get the KD, right? So in this case, the SRT is 5, N is 1, and SRT is 5, and at 50% saturation, right? So under this example, really, there are 5 micromolar binding sites total in the tube. At 50% saturation, half of them are occupied. That's a 2.5 micromolar bound ligand concentration. We subtract out the bound ligand. We get to the free ligand at 50% saturation. That is always KD. Okay, and so this is very straightforward, simple way to look at a binding plot in total ligand and figure out what the KD is, approximate the KD. And so whenever you look at a binding curve for the rest of your lives, the first thing I want you to do is to see whether it's plotted in free ligand or total ligand. If that's unclear from the way some authors have presented it or from your own notes, make damn sure you know whether you're looking at total ligand or free ligand. If it's total ligand, subtract out half the value of your best estimate of the receptor concentration times the cooperativity. And that gives you a KD estimate. And so that's the first thing you should do whenever you're looking at a binding curve. So that's one of the sort of 2 critical points for this whole screencast is this graphical correction and the simple mathematical point that underlies it, which is that at 50% saturation, the free is always equal to KD. So if we subtract out the bound and go to the free, we know the KD. The second key point, though, is how that simple arithmetic enables you to conceptualize binding experiments and actually even design them. And so to do that, we're going to step through 2 other examples. In this case, we have an example where the KD, this curve is simulated using a KD of 2 and an SRT of 5. And so the KD is roughly equal to the SRT. They're not exactly the same, but they're the same order of magnitude. They're rather close in value. And so we're going to call this a regime. We're going to call this a regime of binding experiment design. This regime is the regime where SRT is rather similar in value to KD. The next regime we're going to consider is when SRT is much small, right? So this is the regime for this first analysis. I'm sorry. I have the trackpad is basically broken, and because you guys need this, I'm forging ahead with this. I apologize that there's some flakiness to it. But anyway, so this is the regime that we first analyzed. We have significant free and bound ligand at 50% saturation. So at 50% saturation, the free ligand is roughly equal to the bound. The free ligand is the KD. That's in here. Right? If we just think about the distances along the total ligand axis, we think about the distribution of total ligand, right? The total ligand concentration in here, represented by this distance, that's the free. That is KD. The bound is represented by this distance. That is. We need to sum them to get total ligand, right? Sum of free and bound gives you total ligand. Bound is in here, free is in here. The magnitude of bound and free is roughly similar. This is the regime where KD is roughly similar to SRT, and therefore at 50% saturation, you have an appreciable amount of ligand. You have relatively similar amounts of ligand, both free and bound. Okay, so that's regime 1. Now, to think more broadly and deeply about how binding experiments work and how we should design them, we're next to consider a regime where SRT is much lower than KD. And so that's shown in the next graph. So this graph now shows simulated data for a receptor with the same KD, 2.0 micromolar. But now SRT, rather than being 5 micromolar, SRT in this case is 0.1 micromolar. So 0.1 micromolar is 1/20th of the KD. At 50% saturation, only half of the receptor is occupied, and so the amount of bound ligand is going to be 1/40th the KD under this condition. So the key point is we have first considered an experiment where the SRT concentration is roughly similar to KD. Now we're going to consider an experiment where the SRT concentration is much less than KD. The same graphical correction principle still works. This graphical correction always works. The KD is always, it's 50% saturation. If you find the total ligand concentration and subtract out your estimate of bound, that's going to give you a good estimate of free. The free at 50% saturation is always the KD. The graphical correction always works. And once you figure out whether you're looking at a free or total ligand axis, the first thing you always want to do is graphically correct. The graphical correction here is NSRT over 2, or 0.05. So how big is 0.05, on this length scale? Well, 0.05 on this length scale is probably about the thickness of a tick, again. So the graphical correction in this place is not entirely imperceptible, but it is basically insignificant. So under this condition, right, the same math always will hold. The total ligand is the free, which at 50% saturation is the KD, plus the bound, which at 50% saturation is NSRT over 2. The KD then is always going to be the total ligand at 50% saturation minus, half of the total receptor concentration. If the total receptor concentration is tiny compared to KD, right, the free ligand at this point has to be KD. You have to have at least KD in your tube to get 50% saturation, right? Because you have to have at least KD of free ligand in your tube to get 50% saturation. You need KD, you need a free ligand concentration of KD to get 50% saturation. So you have to have at least that much ligand in your tube. If you have a very small amount of receptor compared to KD, well, that means quantitatively there's just a really tiny amount bound here, right? The free is 2 micromolar. The bound under this condition, where SRT is 0.1, it is only 0.05, right? 0.05 is a very small amount on this length scale. And so the graphical correction is tiny. So arithmetically, I hope that's straightforward. What does it mean conceptually? What it means conceptually is that if you have, a very small amount of receptor compared to the KD, in a binding experiment, the free ligand concentration has to go through the KD. If the receptor concentration is very small compared to KD, there's going to be a very small amount of bound ligand at 50% saturation. That means there's a very small graphical correction. More generally, it means there's a very small displacement between the free ligand curve and the bound ligand curve. That point's going to be made in the next a few slides from now. We're going to illustrate that graphically. But the most important thing is to understand it conceptually. In this case, the graphical correction always works. In this case, the graphical correction is basically insignificant. And so if you look at the total ligand curve and you go to 50% saturation, the total ligand is almost equal, is very, very similar to the free ligand, right? The total ligand is always the free plus the bound. At 50% saturation, free is KD. If bound is tiny, right, this axis is going to approximately be equal to the free ligand concentration, right? So when the receptor concentration is very, very small compared to KD, because the binding curve has to go through a free ligand concentration equal to KD, if the receptor concentration is very small compared to that, there's going to be a small difference between free and total. And so what that means under these circumstances, the total ligand is roughly equal to the free, right? The graphical correction is tiny, and that means the total ligand concentration only needs to be corrected by a tiny amount. That means the total ligand concentration is roughly equal to the free ligand concentration, right? So in this regime, where the receptor concentration is very small compared to the KD, the total ligand is approximately equal to the free ligand, and this is therefore approximately a curve in free ligand, right? There is some small displacement between them, but if that displacement is so small that you cannot see it on the scale of your plot, right, this is effectively equivalent to a plot in free ligand concentration. All right, so that's a very important point. If SRT is much less than KD, this regime of performing a binding experiment is optimal for KD determination. Why? It's optimal because the total ligand is just about equal to the free, and as you look at the data, as you plot the curve, as you analyze the data, it's a good approximation to just use the binding curve at the binding equation that describes free ligand. You can just look at this midpoint. you should mentally think through the graphical correction. You see the graphical correction is incredibly small. And so although this is total ligand is quantitatively about equal to free ligand. And so this curve, basically this axis to a certain extent, although it is total ligand, it is approximately equal to free ligand. And binding curves in free ligand are mathematically very simple. The 50% saturation, free ligand at 50% saturation is always equal to Kd. In this regime, the total ligand curve really is approximately the same as the free ligand binding curve, and this is a simple situation for analyzing dissociation constant. Now, so what happens when we put in more receptors? So we go from this regime, total receptor is much smaller than Kd. You have a minimal displacement between free and total ligand. We now put in more receptor. So if we put in more receptor, we now have a larger displacement between free and total ligand. And we have to do the graphical correction to get a decent estimate of Kd. Okay, so again, into this regime, there's negligible ligand bound, and L total is about equal to L free because the receptor concentration is very small compared to this concentration scale. The concentration scale in a binding experiment has to move through the Kd because you have to have a free ligand concentration equal to Kd at 50% saturation, and therefore you need minimally LF equal to Kd. Minimally you need a total ligand equal to Kd, right? Because the free is smaller than the total. The free at 50% saturation has to equal to Kd. The total at 50% saturation has to be at least or something greater than Kd. So if the SRT is much less than Kd, the free ligand is about equal to the total. But as you add in more and more receptor, you get a bigger and bigger displacement between the free and the Kd. The shape of the binding curve changes. The graphical correction becomes very important to actually get a good estimate of free ligand concentration. But if we consider the simple mathematical relationship, which is the total equals free plus bound, we can then take the total, subtract out the bound, get the free, and still get a good Kd estimate. But now let's consider what happens if we go to an even higher concentration of receptor. Well, qualitatively, if we put in more receptor, this displacement between free and total ligand is going to get even larger. So let's go ahead and do that. So this curve now is simulating data that has been acquired with a total receptor concentration of 50 micromolar, right? So now we have 50 micromolar total receptor concentration, or SRT. That is much, much greater than the Kd of 2. It's 25 times greater. And so what we have is a much larger displacement between free and the total ligand. You'll notice the total ligand axes here are the same, running from 0 to 10. The total ligand axis here is much larger. The total ligand axis here is running from 0 to 80. Right, so we've had to change the axis scale. At 50% saturation, well, the total ligand will still be the free plus the bound, but at 50% saturation, with 50% saturation, if we have 50 micromolar receptor, 50% saturation, we need at least 25 micromolar ligand to be 50% saturated the receptor, right? If we have 50 micromolar receptor, we need at least 25 micromolar receptor to saturate it. We need exactly 25 micromolar receptor to occupy half the binding sites plus Kd worth of free ligand, right? And so if we do the graphical correction here, we're going to subtract out 25. 25 is going to bring us back to the free ligand concentration at 50% saturation. That's Kd. That's still 2, right? All these experiments are working with the same receptor under the same experimental conditions. We can still do the graphical correction. It will always work, but in this case, the graphical correction is much, much larger. I should say I've been greatly impeded in making screencasts for the last 24 hours because the pen has generally not worked. Suddenly, as I was talking into my screen here, the pen started working, so I can now circle this to highlight for you the graphical correction. 5 minutes ago, I was unable to do that because the pen refused to come up or work. such as the wondrous world of computer software. It's great when it works, and it's just miserable when it doesn't. Anyway, it's now working better. We'll see how much longer it continues to work. Okay, so this is now the graphical correction still works, but now the graphical correction is huge. We do the graphical correction, we follow it down to the ligand concentration axis. We do the graphical corrections, we come down here. The principle still works, right? We do the graphical correction, we come down, we do the graphical correction, that will give us the free ligand at 50% saturation. Sorry, the free ligand at 50% saturation is still equal to KD. We can come down to this axis and we can get a good estimate of KD. With these simulated data where everything is perfect, I do the graphical correction, I come down my KD is exactly 2. That's what I put in the simulation, everything works perfectly. But I think you should be able to see that with noisy data, you'd already have a problem. If we had a little bit of noise in these data, figuring out exactly where we came to with 50% saturation would be a ambiguous business. We're coming down very, very close to the origin. We have a very low ligand concentration. On this scale, 2 micromolar is pretty low compared to this axis scale that goes up to 80. With perfect data, we can still sort of get a good estimate of the free ligand concentration. But now consider what would happen if the ligand concentration consider what would happen if we have some noise in the data. If we had noise in the data, this graphical, and let's say we were just a couple micromolar off in our estimate of the free, of the total, if we were just a few micromolar off in our estimation of where the 50% saturation point is, even if we have incredibly reliable estimates of total ligand concentration, in some experiments would have noise there too, but assuming for the moment we have a really good estimate of total ligand concentration, but if the binding curve is noisy, right, if our signal is noisy that we're using to infer the 50% saturation point, we might have some uncertainty in where 50% saturation takes place, right? With some uncertainty in that parameter, when we do the graphical correction, well, in some case, it might even lead us back into the negative ligand territory. What does that mean? Well, negative ligand is physically impossible. What that's saying is that the graphical correction is bringing us back to close to 0. Right? So basically on this concentration scale, if the data were noisy, the only thing we might be able to say is that the total ligand concentration is close to 0. Well, on this scale, 2 micromolar is close to 0. But, like 1 nanomolar would be close to 0. 1 femtomolar would be close to 0. The bottom line is at a certain point, all we'd be able to see after doing the graphical correction is that the free ligand concentration, the KD, is close to 0 on this scale. With perfect simulated data, we can do a precise correction and see that it's 2 micromolar KD. With noisy data, all we may know is that it's somewhere between 0, meaning attomolar, femtomolar, nanomolar, and, a couple micromolar. And so we'd have a huge amount of uncertainty in the total ligand concentration. We'd have a huge amount of uncertainty in the free ligand concentration. The free ligand concentration at 50% saturation is equal to KD, right? Now here, the free ligand concentration is about equal to the total, right? In this case, there's just an insignificant difference between free and total. And so the free is about equal to the total. We run through the binding experiment. Even if the data were noisy, because the free ligand is about equal to the total, we're not going to have much uncertainty in what the free is. And therefore, we're going to have a good estimate of KD. So this regime of SR total much less than KD is optimal for KD determination. This regime of SRT being way higher than KD is problematic for KD determination if there's any noise in the data. Now, it turns out it is good for something else. It's good for determining stoichiometry. I'm going to explain that next. But I want to pause here because the essential conceptual content of this whole screencast has now been covered. The bottom line is the graphical correction reflects a simple mathematical principle, was that at 50% saturation, the free ligand is always equal to KD. If we take the total ligand at 50% saturation, subtract the bound, we're going to get the KD. So that's a simple way for us to go from any binding experiment. Once we are sure that someone is plotting total ligand, we can take any binding data, we can do the graphical correction, we can get an estimate of KD. In some cases, we're going to have in some cases, we're going to have an extremely robust estimate because that correction is negligible, because under this, in this regime, LF and LT are about the same. We don't have a significant amount of receptor on this concentration scale, so there's just not a significant difference between free and bound, and we get a very robust estimate of KD. In this concentration scale where KD and SRT are about equal, we still can get a decent estimate. In this regime where SRT is way, way greater than KD, the graphical correction is so high that within a little bit of noise, all we're going to be able to do is say that on this concentration scale, KD is low. With a little bit of noise, we might, we will still be able to say it's low compared to 20 micromolar or 40 micromolar, but we might not be able to really distinguish 2 micromolar from 0.0001 micromolar, right? And that is a huge difference in affinity, right? So this regime is problematic for measuring dissociation constant or affinity. This regime of experimental design is ideal for measuring affinity. That's the key point of this. Those are the key points of this whole section of the screencast. This simple arithmetic principle lets you both analyze any binding experiment quickly to get a rough idea of the dissociation constant. By subtracting out the bound, you get to the free at 50% saturation. That gives you an estimate of KD. It also, that simple principle also lets you to understand the key parameter of experimental design, right? If SRT is large compared to KD, the graphical correction is going to be huge. In this case, the free ligand at 50% saturation is insignificant compared to the bound. With a little bit of noise, we're not even going to be able to tell exactly what it is. We're only going to be able to tell it's small compared to the amount of ligand that we have in the tube and the amount of receptor we have in the tube. In this regime, on the other hand, the amount of bound receptor is tiny. The free is, the total is mostly free. And in this regime, we're going to get an excellent, robust estimate of dissociation constant because total is about equal to free. Free at 50% saturation, therefore, can be read off just the total ligand axis because they're about the same. We get a great estimate of KD. Those are the essential points for this section of the screencast. If you understand this, you will interpret binding experiments in the literature correctly. You will design your experiments correctly, and those are the most important things. Okay, but now we're going to go on and look at some slightly more complicated things. And so the first thing we're going to do is focus on the fact that this kind of experimental regime actually is very good for measuring stoichiometry. We haven't talked about stoichiometry in detail, to talk about it really rigorously, we're going to have to consider carefully its relationship to cooperativity. That's a bit complex, and so we're going to defer that to later. For the moment, let's just consider stoichiometry as a linear scale factor for the total receptor concentration. The underlying critical point here experimentally is that estimates of total receptor concentration are often very inaccurate. I'll talk about this in a bit more detail later, but the bottom line is the measurement methods to determine protein concentration aren't great. They tend to be rather imprecise. It's very hard to know receptor concentration, protein concentration with better than about 10% precision. We'll talk about what precision means technically in the next course module. For the moment, it's sufficient to say that receptor concentration estimates are themselves noisy, and that can lead to 10 or in some cases even 20 or 30 or 40 or 50% uncertainty in which a receptor concentration is. There's another fundamental complication in biochemistry in that proteins are aggregation prone. This is actually the underlying cause of a significant number of human diseases, including prevalent and important diseases like Alzheimer's disease. Proteins are aggregation prone. In the body, relatively few proteins are, aggregating. Actually, probably a lot of proteins are aggregating, but there are biochemical systems that deal with that. That process can get out of control in conditions such as Alzheimer's disease. In the test tube, because you don't have those biochemical systems that control aggregation and other factors I'll talk about briefly later, in the test tube, proteins can aggregate. So you can lose protein during the course of the experiment even. And so that's another reason. Your protein receptor concentration can be significantly off. Your concentration of active receptor between the inaccuracies in quantification and the loss of activity of the receptor, the active receptor concentration can be quite different from your estimate, right? And so that means the total concentration of active receptors can be different from your estimate of receptor concentration. So our total here is supposed to be your estimate of receptor concentration. S, or stoichiometry, is the scale factor relating total receptor concentration to actual active receptor concentrations, right? And this may seem a little bit funky, but experimentally this is extremely important, again, because receptors can have a purified receptor can have an inactive population. Its quantification can be inaccurate, right? And so what we'll see here, this binding curve is dominated by the amount of receptor we have. If our receptor concentration estimate is off, right, well, then there's going to be some complication in interpreting this, right? If we don't know what the total receptor concentration is, we can't do the graphical correction. So if we don't know what the active receptor concentration is, we can't figure out how many binding sites are bound at 50% saturation. We cannot do the graphical correction even effectively. So it's important in many cases to know what the actual receptor concentration is. Because of inactive protein and inaccurate quantification, our estimate of total receptor concentration, which is given by R total, can be off. S, or stoichiometry, is a linear scale factor that gives the actual active protein concentration. Stoichiometry is the ratio, effectively, of actual active protein compared to our estimate of protein concentration. So S times RT, the product, is the actual active protein concentration. RT is our estimate of the total protein concentration. So now let's think about what this means. Sorry, I should have brought this legend up earlier, right? We're now going to focus on the regime where SRT is much greater than KD. That means there's negligible free ligand, right? On this concentration scale, there's negligible free ligand. Under these circumstances, we basically can measure stoichiometry. And so now what we're going to do is focus on, the next slide essentially is focusing on how and why that is that we can use this to measure stoichiometry. All right, so let's focus on this. The math here is pretty simple. I know when students first see this, they're often a little bit confused by it. We're once again in a situation where the arithmetic and the algebra aren't really complicated, but the conceptual factors involved in the analysis, are well, a little bit tricky. It's the kind of reasoning, once again, that many of you have not engaged in frequently, at least not in the recent time period in your education. So I think one thing it's always worth doing is considering things qualitatively. What happens when SRT is much greater than KD? Well, we talked about earlier how KD was the normalizer or metric for the binding experiment, right? When free ligand is 50% is equal to KD, you get 50% saturation. Total ligand is always going to be bigger than free ligand, right? So to get 50% saturation, we're always going to need total ligand to be greater than KD, right? So when total ligand gets very large, when total receptor gets very large, what happens, right? When total receptor gets very large, let's think about this in terms of the chemistry. And let's go back to the principle of mass action that you probably first heard about in high school and maybe even in grammar school. The principle of mass action says that when one reactant is very high in concentration, it pushes the reaction. I'm sorry, I would like to circle this, but the pen, now it suddenly works again, sorry. Okay, so what we're going to consider now is the situation where the total receptor concentration is very large, right? So I'm going to schematize that by putting in this arrow. What this is supposed to mean is the total ligand concentration is very high. Well, what does high mean? High means compared to KD. The KD is the normalizer for the concentration dependencies in a binding experiment. If SRT is much greater than KD, that effectively means high. If SRT is much greater than KD, and in particular SRF is much greater than KD, if SRF is much greater than KD, well then SRT has to be much greater than KD. And what's going to happen? By mass act, right? If SRF is very high by mass action, it pushes the reaction in this direction, right? So this is an important qualitative consideration. When SRF is much greater than KD, by mass action, we push the reaction forward. We push the reaction to the complex state. What does that mean? Well, effectively, that means at some point, right, if SRF is very high, we will saturate the ligand with receptor, right? We're used to thinking of the binding curve at high free or total ligand concentration. With high free or total ligand, we saturate the receptor with ligand. If the receptor concentration is very high, we instead saturate the ligand with receptor. And that's qualitatively what's happening under these circumstances. At the start of a binding experiment, right, if we consider what's going on here, right, this is the zero total ligand point. Well, when there's no ligand at all, the free receptor is equal to the total receptor. So I'm going to repeat that because that's an important point. When there's no ligand at all in your test tube, the total receptor is all free. So the free is equal to the total. If that free receptor concentration is very high compared to KD, by mass action, you will basically push saturation of the ligand. When free receptor is very high, the ligand will be saturated, and the ligand will be pushed entirely into the complex form. So qualitatively, that's what's happening in this regime of SRT much greater than KD. If SRT is much greater than KD, well, at the start of the titration, that's all free. That means the free receptor is much, much greater than KD. The free receptor, therefore, saturates the ligand. The ligand is driven almost entirely into the bound state. So that is what's happening here. In this regime of conducting a binding experiment, at the outset of the binding experiment, almost all the receptor is free. If the total receptor is much greater than KD at the outset of the binding experiment, the free receptor is KD. So what happens is every time we make an addition of ligand, we add a little ligand here. It's saturated by receptor. We add more ligand. It's saturated by receptor. We add more ligand. It's saturated by receptor. We add more ligand. It's saturated by receptor, right? What's going to happen is until the free receptor concentration falls below the KD, every time you put in more ligand, right? As long as the free receptor concentration remains high compared to KD, the receptor will saturate the incoming ligand, and then we're going to get all of the ligands going to be bound, right? We're going to continue to get all of the incoming ligands saturated by receptor. So what happens there is you get a linear increase in the fractional saturation, because for every aliquot of say you add in 10 equal aliquots of ligand. Every time you add an aliquot of ligand, as long as the free receptor concentration remains high compared to KD, that aliquot of ligand is saturated, it's all bound. So 10 equal aliquots of ligand, 10 equal steps up in the concentration of bound receptor, because all of that incoming ligand is bound. It will continue to be bound until you titrate up enough of the receptor that the receptor concentration falls compared to KD. All right, so let's think about this mathematically. I'm just going to now say exactly the same. I'm going to make exactly the same point that I've made qualitatively, right? Until what I've talked about for the last few minutes is the law of mass action, saying if free receptor is very high, you saturate incoming ligand. How do we see that mathematically? Well, for n equal 1, KD equals SRF times LF over SRL, right? So let's rearrange this. SRL over LF, right? So we're taking this ratio, we're just moving it to the other side of the equation. SRL over LF, is going to be SRF divided by KD, right? So we're dividing through by KD, and we're taking this ratio over to this side of the equation. So we get the ratio, right? So what is this? This is the ratio of bound to free ligand, right? Bound to free ligand. We take that ratio over to this side of the equation. We divide through by KD. The ratio bound to free ligand is going to be the free receptor concentration over the KD. Early in a binding experiment, the receptor is going to be mostly free. If SRT is much greater than KD, right? At low saturation, the free receptor is about equal to the total receptor, right? Down here, we have 50 micromolar receptor. We have only, 5 micromolar ligand. Even when all of the ligands bound to receptor, we're still, right? We have 5 micromolar ligand. Even if it's all bound to the receptor, we still have 45 micromolar receptor, right? The receptor, the free receptor, is still 45 micromolar. It's still similar to the total receptor. It's still usually higher than Kd. So at low saturation, the free receptor is going to be similar to, approximately equal to the total receptor. Well, what does that mean? If SRT is much greater than Kd under these circumstances, SRF is going to be much greater than Kd, right? And so what that means, right, if SRF is much greater than Kd, right, if SRF is much greater than Kd, this ratio is much greater than 1, right? And so what that means is SRL over LF is much greater than 1, right? SRL over LF is going to be given mathematically by SRF over Kd. At low saturation, the free receptor is about equal to the total. If the total is way huger than Kd, the free is way huger than Kd, this ratio is much greater than 1. And that means that the ratio of bound to free ligand is much greater than 1. Right? So what we're seeing here is something that's sort of reciprocal to what we've seen with ligand in other cases. The ratio of bound to free receptor is given by the ratio of free ligand to Kd. We've seen that in the math we looked at earlier. Well, for n equals 1, this interaction is completely reciprocal, right? And so therefore what applies to ligand applies to receptor. If the bound to, so in this case, the bound receptor to free ligand concentration is going to be equal to the ratio of free receptor to Kd. If the total receptor is much higher than Kd, at low saturation, that means the free receptor is going to be much higher than Kd. If the free receptor is much higher than Kd, this ratio is much greater than 1, and that means the ratio of bound to ligand to free ligand is going to be much greater than 1. So this is just algebraically making the point that I made earlier with mass action. Under this regime, where SRT is much greater than Kd, at low fractional saturation, the free ligand is going to be, the free receptor concentration is huge compared to Kd. That is going to mathematically mean that the ratio of bound ligand to free ligand is much, much greater than 1, right? In the example given here, even at 5 micromolar total ligand, it's going to be almost entirely bound. We'll have 45 micromolar free. If our Kd is 2, that's a ratio of 22 to 1. Right? So even at this point, what we're going to have is you're going to have a 22 to 1 ratio of bound ligands to free ligands. So as additional ligand comes in, it's going to partition into the bound state 22 to 1. This is just recapitulating algebraically what I said before in terms of qualitative chemical analysis. Under this condition, with a lot of receptor compared to Kd, the receptor saturates the ligand, the incoming ligand is all bound. Okay. So high receptor concentration compared to Kd, the receptor saturates the incoming ligand by mass action. We can prove that or consider that algebraically with this kind of math. And now what we can do is use this mathematical relationship to understand how we can use this plot to measure stoichiometry, right? So fractional saturation is given by SRL over SRT, right? Under these conditions, what we have is that under these conditions, too soon. Under these conditions, the incoming ligand is saturated by mass action, right? That means that the bound ligand concentration is about equal to the total ligand, right? What we're saying here is that if the receptor is saturating the incoming ligand, the bound ligand concentration is about equal to the total ligand concentration, right? So under these circumstances, where the receptor is saturating the ligand, SRL is effectively given by L total. So under these circumstances, fractional saturation is given by L total over SRT, okay? And so what that means is that if we think about this, what are we looking at here, right? Well, so this is fractional saturation as a function of total ligand. What this equation tells us, what this analysis and this math tells us, is that fractional saturation is basically linear related to total ligand concentration by a factor of 1 over SRT, right? So what we expect based on the mathematical analysis, right? The mathematical analysis is just reflecting our qualitative analysis that's saying that by mass action, incoming ligand is saturated by receptor. Under that condition of, again, by mass action, when we have the incoming ligand being saturated by the receptor, what that means is that the bound ligand concentration is pretty much equal to the total ligand. All of the ligand is going into the bound state. The bound ligand concentration, which is equal for n equal 1 to the bound receptor concentration, the bound ligand concentration is going to be equal to the total ligand concentration. That means fractional saturation is a linear function of total ligand. That's what we see in the simulated data. The fractional saturation is a linear function of total ligand. The slope of that linear function is SRT. So if we do a binding experiment and we normalize to fractional saturation, we do a binding experiment under this regime, where SRT is much greater than KD. We should see a linear dependency on the incoming ligand. We get that linear dependency because incoming ligand is all bound up as soon as it comes in, right? Until we've depleted the receptor and the free receptor falls down to a lower value. With a free receptor, for a significant range of the titration remains very high compared to the KD. The free receptor, therefore, continues to saturate the incoming ligand. Every time we put in a little bit more ligand, it all gets bound, and we see a linear relationship between fractional saturation and total ligand, as that total ligand is all bound to the receptor, and the slope of that line is given by 1 over SRT. So if we take a binding experiment, conducted under these conditions, where the total receptor concentration is much bigger than the KD, right, we expect a straight line. If we conduct a binding experiment that way, we see the straight line, we normalize to fractional saturation, right? This math is now applying importantly to fractional saturation. We target our experimental data, we see this linear dependency, we do the graphical correction, it tells us that the KD is much, much less than the SRT. We're working in this regime. We now normalize to fractional saturation, we normalize our data to fractional saturation. That slope gives us 1 over SRT, right? So if we have an estimate of RT, that's what RT is supposed to represent, our experimental estimate of receptor concentration, but the slope here is SRT. If we divide that slope by RT, we get stoichiometry. This kind of experimental design or situation enables us to measure stoichiometry. We measure stoichiometry to loop back and try to put all the pieces together. We're measuring stoichiometry because when all of the ligand is bound as it comes in, if we know what fraction, right? In the end, if we do the experiment and we know where we get complete saturation of the receptor, right? What we know in essence is we know that this much ligand has saturated that fraction of the receptor concentration. When we know what that ligand concentration is, right? So look, come on in here. We know that in this case, it's taking something on the order of 5 micromolar ligand it takes about 5 micromolar ligand to saturate 10% of the receptor. So we know that we have basically, right, all the ligand is bound. That means 10% saturation of the receptor is achieved when we have 5 micromolar bound receptor. 5 micromolar bound receptor is 10% of the population. Total receptor has to be 5 times that, or 50 micromolar. So mathematically, none of this is complicated, right? This is very simple algebra, very simple consideration of limiting conditions. Mathematically, this is really pretty easy. Conceptually, I admit it is not really easy. To tie it together conceptually, I recommend you refer back to the law of mass action. You just keep solidly in your mind that under these conditions, when you have a ton of receptor compared to KD, that means when there's relatively little ligand in the solution, you have a ton of free receptor compared to KD. That means the free receptor is going to saturate the incoming ligand. All of the incoming ligand is bound. When we know, therefore, we know basically what the concentration if we know the ligand concentration, we know the concentration of bound receptor. because it's equal to the total ligand concentration under these circumstances. If we know and that means we know the absolute concentration of bound receptor. If we know what fraction that is of the total receptor concentration, we know the total receptor concentration. Because the total receptor concentration depends on the stoichiometry scale factor, we can determine binding stoichiometry. So again, it can be a little bit tricky to hold this all together in your minds. I think the most important thing is to understand the principle. The principle is that when total receptor is very high compared to KD, at the outside of the titration, it's almost all free. It will saturate the incoming ligand. And then, once you understand you're saturating the incoming ligand, you can understand this linear dependency. You can crank through the math. You can see that on the fractional saturation scale, the scope is over 1 SR total. And so then mathematically, you can use this rather simple algebra basically to see how you can mathematically get an analysis of total receptor concentration. So, important point here. In this regime, where SRT is much greater than KD, we started by considering that the graphical correction is so large that with a little bit of noise in the data, we're going to have an enormous amount of uncertainty in KD. So this is not a good regime for determining KD. What we've just explained is that it is an excellent regime for determining stoichiometry, or basically measuring SRT empirically. All right, so let's try to tie all this together. Let's go through this just focusing on, so I've brought back the graph showing the other regimes of the binding experiment, and let's just step through it again. Let's start with the one regime that we just looked at. When SRT is much greater than KD, the incoming ligand is basically saturated by the receptor. When we do the graphical correction, it's going to lead us back close to the origin with a little bit of noise in the data. That's going to be unstable a situation in which to determine KD. It's going to be a very good situation in which to measure this slope and determine stoichiometry, but an unstable way to measure KD. The graphical correction tells us that, makes that point, right? We still want to do the graphical correction. It makes the point that we don't, that we're going to have trouble at, right? It makes the point that the KD is low on the scale of our experiment, on which our experiment is connected. If the KD is low on the scale, we're going to have a hard time quantifying it from these data. The fact that the KD is low means the free is low. That means almost everything is bound. So the graphical correction effectively tells you both of those things. It tells you there's a tiny amount of free on this concentration scale. That tells you that almost everything is bound on this concentration scale. That tells you you're in a bad regime for measuring KD, but a good regime for figuring out how much receptor is there because all the ligand is bound. The graphical correction tells you both of those things. We come now down to this regime that we looked at earlier, where the free ligand is about equal to the KD. In this regime, the graphical correction works. In this regime, we should be able to get a decent estimate of KD. If we have uncertainty about stoichiometry or uncertainty about cooperativity, this measurement may be a bit uncertain, but still we should be able to get some information about KD, and especially if n is equal to 1 and the stoichiometry is at least reasonably close to 1, we're still going to get a pretty good KD estimate. On the other hand, in this circumstance, the free ligand, right, where we have a tiny amount of receptor, the graphical correction is tiny. So in the same way that the graphical correction here tells you that almost everything is bound and very little is free, the graphical correction here tells you that almost nothing is bound and almost everything is free. In this case, the graphical correction is insignificant. It doesn't really matter what n is, doesn't really matter what s is. If the receptor concentration is really, really small, n could be higher than 1, s could be higher than 1. If the receptor concentration is 1/100th the KD, even if ns is 5, NSRT would still be 1/20th of the KD. It's still a tiny correction, right? It still means that under this circumstance, we have a very, very minor correction. We have a negligible correction, and that means we can just, total, right? The graphical correction tells us that the free ligand is about equal to total, right? graphical correction here is tiny. This is a tiny graphical correction. It means free is equal to total, roughly. If free is equal to total, we can even use that old, the simpler binding equation that we used earlier, right? And when you come through 56% saturation, even with very noisy data, we're going to be able to see, reasonably well where we're getting what the ligand concentration is. Because that's all free, we're going to get a reasonably good estimate of KD. Over here, we have a huge graphical correction. It means everything is bound. It means our SRT is, it means our free ligand concentration is close to the origin. It could be so close to the origin that we have even orders of magnitude uncertainty in free ligand concentration, and therefore orders of magnitude uncertainty in our KD. And the graphical correction then is telling us that everything is bound. If everything is bound, right? If everything is bound, that we know, right? We know that at this total ligand concentration, basically half of the receptor is bound, and that that this total ligand concentration, because all the ligand is still, the ligand is almost all bound. The graphical correction tells us the ligand is almost all bound. That means that we know the bound receptor concentration because we know the ligand concentration. If we know the ligand concentration and the ligand is all bound, almost all bound, we know the bound receptor concentration. If we know that this concentration of ligand is right, this concentration, let's look at that. Simple point here, we're still in the region where we get a linear dependency of fractional saturation at KD. We come down, right? Sorry, I'm not very good with the trackpad. We come down, right, under this regime. Right, we get the midpoint in 50% saturation at roughly 25 micromolar. We can see, because we're still in this linear regime and we do the graphical correction, we know that most of the ligand is bound. We know basically that 50% of the receptor concentration has bound 25 micromolar of ligand. That means that 50% of the receptor concentration is basically 25 micromolar. That means that 100% of the receptor concentration is 50 micromolar. So getting all of the details sort of organized in your mind on this, there are significant complexities here. The graphical correction, which relates to this, the simple principle, total is equal to free and bound. At 50% saturation, free is KD, bound is half of the total receptor concentration, right? This graphical correction is practically the most important thing to do when you're analyzing data. Also, if you understand it, it's a good organizing point for thinking about qualitatively what's happening in the experiment, understanding that in this situation, almost all of the ligand is bound. That means if almost all the ligand is bound, that means we can get a good estimate of how much receptor is there, because we know that at 50%, when 50% of the receptor is bound, that took 25 micromolar ligand. Therefore, we need, roughly half of the receptor concentration is 25 micromolar. The full receptor concentration is 50 micromolar. This mathematical relationship encodes that simple arithmetic point algebraically, right? And now we come down to this regime. The graphical correction is minimal. LF, if the graphical correction is minimal, the free is about equal to bound. This is basically an approximation in LF binding curve. This is a great way to determine KD. Now, when we're in this intermediate regime, right, we can still get a good estimate of KD. The displacement of the curve, and therefore the shape of the curve, depends on both S and RT. In this regime, we can, in principle, estimate both KD and S. So this can be powerful under this regime where LF is, where SRT is about equal to, right, this regime, SRT is about equal to KD. This regime here, right, SRT is about equal to KD, right? In this regime, we can still get a decent estimate of the KD, and the shape of the curve, which is determined by this displacement, depends on S. In this regime, we can, in principle, from a single experiment using curve fitting methods, estimate both S stoichiometry and KD. That can be quite powerful. The problem is that analysis is very sensitive to noise. It can work very well, but the estimates are often very noisy. You need incredibly high quality binding data that goes to thoroughly to saturation to really get robust estimates of S and KD from this experiment. But it nonetheless allows you to make approximate estimates of S and KD under a broader set of circumstances. And when the data are really good, you can actually reliably estimate both S and KD. We've covered a hell of a lot of ground here. If you can internalize all of this, you're way ahead of like 95% of practicing biochemists and molecular biologists, and so that's good. It also means that it is probably a bit challenging to hold it all together, but hopefully the graphical correction, again, it's a simple arithmetic principle that hopefully can help you organize the complicated concepts. All right. So now I'm going to go through stuff that, where the math looks a little bit ugly, but that, in fact is just conceptually and qualitatively, this ugly math is just encoding exactly the same thing I was talking about in the last set of slides. So what we're going to do now is this is going to look at the same phenomenon from a slightly different perspective. We're now going to really sort of mathematically consider more generally exactly what we did in the last slide. So we're going to look at the effect of SRT on experiments. We're going to try to understand the effect of SRT concentration on binding experiments by considering the fractional saturation versus L bound, right? And so fractional saturation, as we looked at earlier, fractional saturation, when we normalize LF to KD, all binding experiments look the same, right? This LF-KD ratio gives us a universal description of fractional saturation dependent just on N. Once we normalize to KD, all fractional saturation curves look the same depending only on the N or the cooperativity. Right? So fractional saturation is equal to the bound receptor divided by the total receptor. This simple equation it shows that once we normalize LF to KD, all fractional saturation curves look the same in this reduced coordinate system, dependent only on the cooperativity. All right, now let's think about the implications of this in terms of L bound. So L bound, sorry about that, L bound, the bound receptor concentration, is N SRL. Okay, so why is it N? Well, SRL is the actual concentration of bound receptor. If the receptor has N-fold cooperativity, we need to multiply the bound receptor concentration by N to get the bound ligand concentration. Fairly straightforward. Let's just put concrete numbers on that to try to illustrate the point. Suppose we have 1 micromolar bound receptor, and it's a 2-fold cooperative receptor. That means we have 2 ligand molecules bound cooperatively per receptor molecule. If we have 1 micromolar of that receptor, we have 2 micromolar of bound ligand because they're 2 molecules bound cooperatively. All right, now, this relationship, right, will tell us what SRL, if we multiply through, right here, SRL, right, if we multiply through by SRT, what we'll get is SRT times Y bar equals SRL, right? So SRL is given by Y bar times SRT, right? The total receptor concentration times the fractional saturation gives us the bound receptor concentration. Bound receptor concentration times the cooperativity number of cooperatively bound ligand molecules per receptor, N times SRT times Y bar gives us the bound ligand concentration. Okay? And so now what we're going to do is we're going to say, so the bound ligand concentration is the fractional saturation of the receptor times the receptor concentration, right? That gives us the concentration of bound receptor times N, that gives us the concentration of bound ligand. We divide this equation through now, right? Simple. We divide this equation through now by KD, right? Divide by KD. Divide by KD, right? Divide this by KD. Sorry, divide everything here by KD. What are we going to get? We're going to get L bound divided by KD equals NSRT over KD times Y bar. Okay, so what does this mean? Well, so L bound divided by KD is, right, these are, in a given binding experiment, these are all constant, right? N is the cooperativity, it's a property of the receptor. SRT is the amount of active receptor concentration, that's a property of our experiment. KD is a property of the receptor in the experimental conditions. In a given experiment, under given experimental conditions, for a given receptor, N and KD are constant. In a given experiment where we're titrating ligand onto receptor, SRT is constant, right? So NSRT in an experiment is a constant. What this is saying is that the ratio of bound ligand to KD is linearly proportional to fractional saturation. So this is pretty simple, right? This is a straight line. This variable is a linear function of that variable, right? Very, very simple. right? This is, right, y equals mx plus b. Y, in this case, there's no intercept, right? This ratio is simply linearly proportional to fractional saturation. So what does that mean? Well, straight lines are easy to work with. And so this leads us to some very simple math, right? And so what we can do now is we can consider, right, this very simple relationship. The ratio of L bound to KD is NSRT over KD, all constants, times y bar. This is a constant. L bound over KD is a linear function of y bar. Well, what does that mean? Y bar is linear proportional to L bound over KD, well, and vice versa. We can now just invert this, right? We can just invert this equation in a sense, right? So this shows L bound over KD is linearly proportional to Y bar. Well, that means that Y bar is linearly proportional to KD. That means Y bar as a function of L bound over KD is simply given, right? All we have to do now is Y bar will be L bound over KD times the reciprocal of this ratio. So Y bar is given by L bound over KD times KD over NSRT. Right? We take the reciprocal of this ratio, we multiply through this equation by the reciprocal of this ratio. What do we get? We get Y bar is equal to KD over NSRT times L bound over KD. The math here is simple. What does it mean? Well, it means there's a linear relationship between Y bar and L bound over KD. So now let's go down and look at the key graph. So this is now plotting fractional saturation as a function of either L free or L bound or L total. L total, right? L total is the sum of L bound and L free, right? L free, in this case, we've normalized everything to KD, but KD is a constant for a given receptor under a given circumstance. So what does that mean, right? So L free plus L bound equals KD, right? The sum of free and bound equals KD. So what we can do now is plot on the same graph L free over KD. Well, what is that? Well, this simple relationship we've seen before, right? We know how to, we have a very simple equation that describes Y bar as a function of L free over KD. What this analysis up here has shown is that Y bar is also a very simple function of L bound over KD. Right? Y bar is linear related to L bound over KD. So what we can do, right, this equation that we derived earlier allows us to plot L free over KD. This relationship allows us to plot L bound over KD. L bound over KD is just a straight line, right? There's a simple linear relationship between L bound, sorry about that, and simple linear relationship between L bound over KD and fractional saturation, and that's shown by the red line. To get a plot then of L total over KD, which is where we started all of this, probably 45 minutes ago or something, right? We want to understand how to conceptualize and how to mathematically analyze binding curves, binding isotherms plotted with Y fractional saturation as a function of L bound. Well, we have a very simple equation that describes the relationship between fractional saturation and LF over KD. This shows we also have a very simple equation that describes the relationship between L bound over KD. At a given fractional saturation level, right? At a given level, we take the free at this level, right? And we sum that with the bound at this level. So we sum those two things together, and what do we get? The sum of those two things at that fractional saturation level gives us the KD. This is very simple arithmetic. It's not the kind of reasoning many of you are familiar with, and that means it'll probably take you a little bit of sort of time in the trenches to wrap your minds around it. But what could be simpler than adding two factors together, right? So this is really arithmetically very simple. On the same axis, we plot LF, Y bar, we plot fractional saturation versus LF. We plot fractional saturation versus L bound. Now, at any given Y bar value, we sum together the free and the bound ligand concentrations, and we get the total ligand concentration. It's simple arithmetic. In this case, I've plotted actual, fractional saturation curve for n equal 4 and NSRT over KD equal 2.5, right? In the previous slide, we were considering, how the relative value of NSRT over KD determines sort of the regime of the binding experiment. In this binding experiment, NSRT is greater than KD, although not by a lot, by a little. And so we have, a significant, the total ligand binding curve is significantly shifted from the free ligand binding curve. An interesting point here is that this shift always involves this linear relationship, right? The shift is always linear in y bar, right? What could be simpler than a straight line? It's always linear in y bar. So now, if we think of this as shifting, along the horizontal axis at given points in the vertical axis, at every point, this simple linear relationship tells us exactly how to shift. In this case, SRT is a little bit greater too, but roughly comparable to KD. We have a significant shift. Another way to look at this would be to say, what the magenta curve here shows is basically L total versus KD. I've told you the first thing you want to do whenever you see a binding curve is L total and do the graphical correction. You want to subtract out NSRT over 2. In this case, everything is normalized to KD. So NSRT over KD is equal to 2.5. Half of that would be 1.25. So at this point, what do we want to do? At this point, we want to do a subtract out in this coordinate system 1.25, right? We want to do the graphical correction in this coordinate system. We're at about 2.25. We subtract out 1.25. The graphical correction tells us that the KD is equal to 1. And so the graphical correction principle still entirely works. This mathematical formalism, if you look at all the algebra, it can seem a bit confusing, but look at the principle, right? This simple sigmoidal cooperative binding isotherm, we've looked at it before. It's a very simple mathematical derivation to give us that sigmoidal binding curve of y bar as a function of LF over KD. L bound over KD, right? The bound ligand increases. What does this line say? The bound ligand increases linearly with fractional saturation, right? When you get to 100% fractional saturation, the bound ligand is exactly equal to NSRT, right? At 100% fractional saturation, all of the receptor is bound, right? And the bound is just going to be equal to NSRT. At 50% saturation, half of that is bound. At 25% saturation, a quarter of it is bound. There is a simple linear relationship between the bound ligand and fractional saturation, right? Fractional saturation is a linear function of bound ligand. Bound ligand, of course, right? Bound ligand is linearly proportional to fractional saturation. If you're 100% fractional saturation, all the receptor is bound. 50% saturation, half. 25% saturation, a quarter. The bound ligand is linearly proportional to fractional saturation. So what we can do now is take the simple cooperative binding isotherm and free ligand and add to it along the x-axis or the horizontal axis, the ligand axis, the bound ligand, right? We sum free and bound, we get total. Well, this is straightforward mathematically. It is not particularly straightforward conceptually. I'm going to just flash up the math. This math now, right? Basically, this math describes the magenta curve. This is a completely rigorous mathematical description of L total as a function of KD. I'm sorry, this is a simple mathematical description of L total, the ratio of L total to KD as a function of LF, KD, and NSRT, right? And so this is a complete description of the binding experiment. Now, we cannot easily invert this equation to get fractional saturation as a function of L total, right? L total over KD is a simple closed form function of LF over KD and an SRT, right? L total over KD is a simple function of all the parameters. If we wanted to invert this and get fractional saturation as a function of KD, that would be hard to do. That would be a very messy equation if n is greater than 1. But in this coordinate system, right, this mathematical equation is exactly right. So why do we need to go to the complicated mathematical situation? Let's focus on the simple mathematical situation, which we get by adding up things along the x-axis, right? The fractional saturation as a function of free ligand We know that very easily, and we can describe it mathematically precisely. The bound ligand as a function of fractional saturation is a simple linear relationship of fractional saturation. We sum these terms together, we get the total ligand, right? So this gets back to where we started the whole screencast, right? We want to understand what's going on in when we look at curves with fractional saturation plotted as a function of total ligand. One simple way to look at it is, well, the total ligand is simply the sum of the free and the bound. Whenever we sum up the free and the bound, we're going to get the total. The bound is always a linear function of fractional saturation. This, in the end, is a very simple way for us to sort of conceptualize what's going on. The graphical correction, where we focus at making that arithmetic correction just at the midpoint, the graphical correction is a very convenient place to do it because it actually gives us the KD. If you don't want to think about what happens throughout the entirety of the fractional saturation curve, just go back to the 50% saturation point. We've now done that extensively in the last few slides. It's incredibly simple arithmetic that gets you an estimate of KD and lets you understand the partitioning of bound versus free ligand, which in the end lets you understand what binding regime you're in. Again, arithmetically, this is all rather simple. Conceptually, there are a fair number of things that you'd ideally hold together in your head. All right, let's go on and try to wrap this up. So, point here, when L bound is normalized to the metric KD, all equilibrium binding curves for specific NSRT over KD are identical, right? When we normalize L bound and we normalize L free, all of these binding curves look the same, and they depend only on N and NSRT over KD. In this space, all, right, in our L total over KD, LF over KD, L bound over KD, L total over KD, in this KD normalized space, all fractional saturation curves are the same, depending just on N and the value of NSRT over KD. All right, so now let's get back to the graphs that we considered earlier with the graphical correction. So in this case, to show you that this does work for cooperative binding experiments, I'm going to show you a set of graphs that are very, very similar to the ones I showed 2 slides ago. But for those, and those showed n equals 1 binding isotherms, these show n equal 4 binding isotherms, right? And so what I want to do here is make the point that the approach shown in the last, right, the analyses I did in the earlier slides where I assumed n equals 1 were fairly straightforward. What I want to, and we focused on the graphical correction just at the 50% saturation point. What I'm trying to do now is help you see that when the binding reactions are cooperative, exactly the same principles apply, right? And so that's why in this case, in this slide, I'm illustrating cooperative binding isotherms, right? So this is n equal 4. Now we're in the LF over KD space, right? So in the LF over KD space, when LF is equal to KD, we're at 1, right? So when we normalize to KD, 50% saturation always occurs when LF equals KD or LF over KD equals 1, right? LF over KD versus 1 is the condition for 50% saturation once we normalize to KD. All right, so now in this KD normalized space, all binding isotherms look the same as long as they have the same degree of cooperativity. Here I'm showing a binding isotherm for n equal 4, but it would work equally well for n equal 2 or n equal 8. The shape would just be a little bit different. As we showed in the last slide, you can take that LF over KD binding isotherm, right? We can look at the free ligand, we can look at fractional saturation as a function of free ligand over KD. We can then also look at the fractional saturation as a function of bound ligand over KD. That's a simple linear relationship. When we sum of the two of them together, we get total ligand as a function of KD. So taking this approach, we can sort of see how, right, when we take this sigmoidal curve and then we add each point along the vertical axis, right, when we take each point along the vertical axis and add the blue curve to the red curve, right, so we're adding basically, we're making an addition along the horizontal axis of the blue and the red curves. Let's say that again. at any individual point along the vertical axis, we're going out, we're finding the LF value, we're finding the L bound value, we're adding them together. But if we think of that as an addition of the blue and the red curves along the horizontal axis, we can see how as we add in more and more of this linear function, we're sort of going from a obviously sigmoidal binding dependency to a somewhat flattened, more flattened curve, right? As we add in more and more of the linear curve, we get a more and more flattened curve, right? The graphical correction still works. NSRT over KD is 2.5. Half of that would be 1.25. I go to the midpoint in total ligand, right? This is exactly what I showed you in the previous slide. Sorry, exactly what I showed you in the previous slide. We subtract out NSRT over 2 at the 50% saturation point. NSRT, we subtract out NSRT over KD divided by 2. NSRT over KD is 2.5. We subtract out half of that at the 50% saturation point. We get a value of 1. In this coordinate system, right, the free ligand always has to be 50% saturation. The free ligand at 50% saturation has to be KD, right? So the graphical correction works as it should. It brings us back to a free ligand concentration of KD, which means LF over KD equals 1, right? So all of this fits together properly. The graphical correction still works even in this KD normalized coordinate space. And it allows us to now think in another way about what happens about the relationship between free and total ligand, right? Here is the regime where NSRT is roughly equal to KD, or NSRT over KD is roughly equal to 1, right? The graphical correction works. We can understand the free ligand, the total ligand curve as being the sum of the free ligand binding isotherm, the sigmoidal free ligand binding isotherm, plus the linear relationship between bound ligand and fractional saturation. Okay, now let's come down to this regime where NSRT over KD is much less than 1, right? NSRT over KD is much less than 1 means, right, SRT, if SRT is much less than KD, NSRT over KD is much less than 1, right? In this reduced coordinate system, LF over KD, right, with n equals 4, you have a sigmoidal binding isotherm, right? The free ligand at 50% saturation is always equal to KD. In the reduced coordinate system, right? In the reduced coordinate system, the free ligand at 50% saturation is 1, right? When LF equals KD equals 1, you have 50% saturation. So now in this reduced coordinate system, the sigmoidal binding isotherm crosses the 50% saturation point at 1, which is where LF equals KD. And so now we can, consider the graphical correction. Well, if NSRT over KD is 0.05, divide that by 2, the graphical correction is 0.025, right? It's 0.025. It's 2.5%. The graphical correction is 2.5% of this amount. It is insignificant, right? It's very small. With the tiny bit of noise, it's going to be insignificant. The relationship of L bound to Y bar is still linear, right? But in this case, because there's very, very little receptor, there's very little receptor bound. There is still a linear relationship between free and bound. But in this case, we never have much bound because there's just very little receptor. We still sum together the free and the bound curves along the L total axis to get the, right? We still sum together, right? We still have the same basic math applying. We can take the Y bar versus L free curve and the Y bar versus L bound curve and sum them together. But in this case, there's so little, right? What does this mean? This means that there's very little bound ligand. The receptor concentration is small, so even at full saturation, there's just very little bound ligand. You still have a linear relationship between L bound and fractional saturation, but that linear, but that's just a very small amount. We still can we still can get the binding curve and total ligand by summing together these two, but there's a very small offset between them because there's very little free ligand bound. Now let's go to the other extreme, where NSRT over KD is very large, in this case 25. This is the same condition that we considered earlier in terms of NSRT. In that case, we had a KD of 2 and an NSRT of 50. That does correspond to NSRT over KD equal 25. So we're considering a similar circumstance, only in this case we're considering N equal 4. So we have the same cooperative binding isotherm, right? We have the same curve giving Y bar as a function of free ligand, right? Now, one thing to consider is, have these blue curves changed in any of these graphs? Well, we're using the same axis here of LF over KD, the same axis here of LF over KD. But now we've had to change the axis, right? Well, you know, when we want to saturate 25, when NSRT over KD is 25, we have to go to LF, we have to go to LT over KD of something greater than 25. So we need a much, you know, we're exploring a much wider range of ligand concentrations here. So we need to expand this axis. In this coordinate system, in this reduced coordinate system, LF equal KD, right? In this coordinate system, the free Y bar as a function of fractional saturation is always the same. Let's step back to that moment. It's on the previous slide, the beginning of the previous slide, right? Sorry, right? The beginning of the previous slide. LF, Y bar as a function of LF over KD is always the same, right? This is always the same, and it depends. Y bar depends just on LF over KD and N, right? This relationship doesn't change no matter how much free receptor you're using in the experiment. The relationship between fractional saturation and LF over KD depends only on N. So let's go forward. Right? So we're looking at the same receptor here, right? Effectively. When we normalize to KD, all receptors look the same. So the blue curve is exactly identical, right? That equation we just looked at gives the blue curve in all cases. The fractional saturation versus free ligand equation depends only on LF over KD and N. It doesn't care about SRT. These blue curves are all the same. The point being, when you have a very little amount of receptor, when you want to sum the free and the bound receptor together, right? If you the free receptor versus LF, I'm sorry, Y bar versus free ligand is the same in all of these graphs. Right here, just the amount of receptor is so little, the displacement of the free and the bound curves is negligible. This is what we talked about earlier, right? Under this circumstance, the free ligand, there's very little bound ligand, and so the total ligand is almost all free. And so the free and bound ligand curves in this circumstance more or less overlap. Here we have somewhat more ligand, and we get a displacement. We begin to see the shape of the total ligand fractional saturation curve flattening out. The underlying free ligand relationship is identical over here. These are exactly the same curves. But when we have more receptor, the L bound over KD is more significant, and we get a bigger displacement of the L total curve from the L free curve. Here, once again, we have this blue curve is identical to these blue curves. The relationship between fractional saturation and free ligand is always the same. That blue curve is identical to these blue curves. But now with a lot more bound total receptor, we end up, right? With a lot more total receptor, we end up with a lot more bound ligand. The relationship between bound ligand and fractional saturation is still linear, right? The more fractional saturation you have, the more bound ligand you have. At 100% fractional saturation, you need NSRT bound. At 50% saturation, you need half of NSRT bound, right? There's obviously a linear relationship between fractional saturation and bound ligand. But in this case, because you have a lot of receptor, you have a lot of bound ligand, right? And so we can think of it at the 50% saturation point as the graphical correction, right? The graphical correction now is quite large. It brings us back near the origin. But we can use the same kind of simple arithmetic now at any point, right? Any point along the Y bar axis. We sum the free and the bound, and we get the total. The point here is that the total is now more or less equal to the bound. And so this is really the loop closing consideration. In this regime, where NSRT over KD is much less than 1, right? NSRT is much less than KD, NSRT is much less than 1. The amount of bound ligand is very small compared to the amount of free ligand if NSRT is much less than KD. Our total ligand curve is about equal to a free ligand curve because there just isn't much ligand bound. This is a great regime for determining KD because the midpoint of fractional saturation in free ligand is KD. We can vary directly without any correction. We don't have to worry about the correction here because it's so small. We read off the KD. In this case, right, in this case, the free ligand is about equal to the total ligand. In this case, right, in this case, bound is almost insignificant, free is about equal to total. In this case, free is insignificant, bound is about equal to total, right? In this case, the total ligand curve reflects primarily bound. Most of the ligand is bound, right? The blue curve here is insignificant compared to the red curve. The red curve here is insignificant compared to the blue curve. The total is just about equal to the free. In this case, the free is insignificant and the total is just about equal to the bound. We can loop back to what we were talking about earlier, right? If the total receptor is very high, it saturates the incoming ligand. All of the ligand, right? The free ligand is saturated by the receptor when the free ligand when this free receptor concentration remains high compared to KD. Incoming free ligand is saturated basically in what is, right? So that's the principle of mass action. Here it's enabling us to see it graphically. When NSRT is much greater than KD, the receptor saturates the ligand. Basically, all of the ligand is bound, right? That means the total ligand, right? Close the loop. The total ligand concentration is about equal to the bound ligand concentration. The free ligand concentration is insignificant. So this is coming back in a way to just where we started. It's showing it differently graphically, right? The blue curves here are all identical. These are absolutely identical blue curves because we've normalized LF to KD. This is a universal binding curve that depends only on cooperativity. This happens to show n equal 4. If n were 2, it would be more sigmoidal. If it were 1, it would be less sigmoidal, but the principle would be the same. The fractional saturation as a function of free ligand depends only on cooperativity. For a given receptor with a given degree of cooperativity, these blue curves are going to be identical. What changes is the relevant amount of bound ligand compared to free ligand in the course of the titration. If there's a tiny amount of receptor, there's a tiny amount of ligand bound. The total ligand curve more or less matches the free ligand curve. If there's a huge amount of receptor, the free ligand is insignificant, and the total ligand curve more or less just matches the bound ligand curve. Because y bar is a linear function of bound ligand, under this circumstance, the fractional saturation curve is a function of total ligand. It's basically a straight line, right? Because almost all the ligand is bound, and bound ligand is a linear function of fractional saturation, and vice versa. So in this regime, basically the total ligand curve pretty much is dominated by bound ligand, right? Free ligand is insignificant in this situation. Bound ligand is insignificant when receptor concentration is tiny compared to KD. Free ligand is insignificant when receptor concentration is huge compared to KD, and so we're looking at primarily bound ligand. If we're looking at primarily bound ligand, we can essentially read off the stoichiometry, right? Because the vast majority of the ligand is bound. We can come to this point, that's 50% binding of the receptor. We know if we have this much free ligand, right? We have this much ligand, right? We have this much total ligand, it's almost all bound. This tells us that 12.5 micromolar total ligand saturates half of the receptor concentration, 12.5 L bound over KD is saturating half the receptor. That means the total amount of receptor is twice that, or 25 NSRT over KD. Okay, so important points. Y bar versus LF over KD depends exclusively on N, right? The blue curve here is identical. The scales here are the same, and so you can see very straightforward way that the blue curve is identical. The scale here is different, so you have to take that into account, but the blue curve is identical. This is the same blue curve. Y bar versus LF over KD depends exclusively on N, right? The fractional saturation as a function of free ligand doesn't care about receptor. This is a universal underlying relationship that holds for receptors binding ligands at equilibrium. Y bar versus depends on LF over KD and N and nothing else. the free ligand concentration at a given fractional saturation is always the same, irrespective of the amount of receptor, right? Free ligand over fractional saturation, the blue curve, is always the same, numerically, quantitatively, identical, irrespective of bound receptor concentration. So that blue curve is always the same. That means we can conceptualize how the overall results in a binding experiment conducted in total ligand concentration. We can conceptualize how total ligand depends on Y bar, or how Y bar depends on total ligand, by considering that the LF over KD versus Y bar curve is always the same. When we have a very high NSRT over KD, right, this linear relationship between bound ligand and fractional saturation dominates, right? The L bound dominates here, right? Almost all of the ligand is bound, and so the L total versus Y bar curve looks a lot like the L bound versus Y bar, right? There's very little free, there's mostly bound. In this regime, the total ligand, right, is mostly bound, and we're looking at basically bound ligand versus Y bar or vice versa. In this regime, there's very little bound ligand. We're looking mostly at the free. The blue curve is always the same. In this case, there's just tiny amount of receptor bound. So there's tiny amount of receptor compared to KD. So there's a tiny amount of ligand bound. And so in this case, right, the bound and, in this case, the total ligand and the free ligand are roughly the same. In this case, instead, the bound ligand and the total ligand are roughly the same, because when you have a ton of receptor, although you have the same amount of free ligand at any degree of fractional saturation, that amount of ligand is now very small compared to the bound, and these curves are dominated by the bound. So Y bar versus LF over KD depends exclusively on N, but Y bar versus L bound over KD depends exclusively on NSRT over KD, right? The blue curve depends exclusively, once you normalize to KD, the free ligand curve depends exclusively on N. The bound ligand curve normalized to KD depends exclusively on NSRT over KD. So separating these things out conceptually is, sort of at the core of understanding what's going on in binding experiments and designing binding experiments. So I'm going to just, at the risk of completely nauseating you by the number of times that I have said this, I'm going to say it one more time, because this is really the most important thing you need to learn about binding. And in some sense, the most important thing, like the two most important things you need to know about binding is the free ligand at 50% saturation is always equal to KD. If there's a really small amount of receptor, right? And so once you normalize ligand concentrations to KD, all binding experiments pretty much look the same and depend only on the cooperativity. And once we normalize to KD, if the receptor concentration is very small compared to KD, in this regime, the bound ligand is always small compared to the free ligand. The total ligand versus the fractional saturation versus total ligand is more or less the same, right? It's very similar. Right? Under this condition, the total ligand is more or less equal to the free ligand, right? Because the bound ligand is insignificant on this concentration scale. Under this condition, where NSRT is much greater than KD, the bound ligand, of course, still has a linear relationship to the fractional saturation, but under this condition, almost all the ligand is bound throughout the binding experiment. The underlying relationship between fractional saturation and free ligand is still the same, right? The blue curves are always the same in all of these experiments. The difference is that if you have a ton of ligand, there's an insignificant amount of free ligand, and that then becomes ignorable. The total ligand is about equal to the bound ligand. Under this condition, the total ligand curve is reflecting primarily the bound ligand. The free ligand relationship is always the same, right? This curve is the same exact as that curve. We've just changed the scale. The bound is now dominating. In this regime of NSRT over KD being very much greater than 1, most ligand, the vast majority of ligand is bound. The total ligand curve is basically reflecting primarily bound ligand. You're measuring stoichiometry because stoichiometry determines how much bound ligand you're going to need to get a certain degree of saturation. Over here, the amount of bound ligand is insignificant, and so the total is about equal to free. In this regime, where NSRT over KD is much less than 1, you're pretty much seeing a free ligand dependency, right? The total ligand is dominated by the free. This is more or less, to a first approximation, a free ligand curve. In this case, because the graphical correction still works, but it's negligible, and you do the graphical correction, you can see that, well, the free is pretty much equal to the bound. And so basically, to a first approximation, total ligand is equal to free, and you can use the free ligand equation here. Here, you can effectively more or less ignore the hyperbolic relationship of free, hyperbolic relationship between fractional saturation of free ligand, because there's a very small amount of ligand free. It's almost all bound, and to a first approximation, you can just consider this, the linear increase that you have to have in bound ligand to get increasing degrees of fractional saturation. Why? Because the vast majority of the ligand is bound. The math that we've done so far is all trivial. Holding this all together is complicated, and it may take you, a couple of minutes, maybe even hours, sitting there staring at the screen to hold this all together. But I've now brought this at you in several different ways. We've looked at it from several different angles. All of the angles fit together. This slide is unfortunately complicated in a way, but it does show in one compact place how all of these considerations fit together. If this is too confusing for you, just go back and go back to the slide where it shows the graphical correction, and just think about, right, if this is too confusing at you, go back and focus exclusively on this 0.5 fractional saturation point and think about the graphical correction and try to become comfortable with that. And I think that will take you, well, first of all, practically speaking, that's a huge amount of what you need to know to design good experiments and solve problems in the laboratory. Practically speaking, so practically speaking, that's like, actually maybe the vast majority of what you need to know to understand and consolidate everything conceptually. It's also a good focal point, because once you understand that, I think the rest will fall into place relatively easily. So this epic length screencast is almost over. I'm just going to cover one more slide quickly. As we said earlier, in the regime where SRT is about equal to KD, or SRT over KD is about equal to 1, right? Here it's equal to 2.5. There's twice as much SRT as KD. From an order of magnitude perspective, these things are pretty similar. In this regime, the graphical correction works, as it does in every regime. It shows you that you have, right, that's basically the bound. That's basically the free. The free is, of course, equal to the KD. The bound and the free are comparable here. The shape of this curve depends then both on bound and free. In this circumstance, when the data are very, very high quality, we can use a pretty straightforward mathematical analysis to determine both KD and SRT reasonably well. Right? The previous set of slides focused on the point that when NSRT is much less than KD, that's a great way to regime in which to determine KD. And it's hard to determine stoichiometry. When NSRT is much greater than KD, that's a great regime in which to determine stoichiometry, but it's very hard to determine KD because the the graphical correction brings us back close to 0. And with a little bit of noise, we're not going to be able to tell where we are. This regime, where NSRT is about equal to KD, in this case they have a ratio of 2.5, right? At 50% saturation, you have a significant amount of ligand bound, and you have a significant amount of ligand free. The shape of the curve, therefore, depends both on KD and on stoichiometry. So we can crank through some algebra, which we'll do in another screencast. The screencast that considers binding kinetics will actually crank through this algebra explicitly. For the time being, let's just say that when n equals 1, we can, we've already been through this in class, when n equals 1, we can take this equation and substitute SRF equals SRT minus SRL, and we can take this, we can substitute here, right? We can take the, we can simply crank it, we can set the free receptor to the total minus the bound. We can also set the free ligand to the total minus the bound. When we multiply that together, we get a quadratic equation. We can solve the quadratic equation. The quadratic equation is, the solution to the quadratic equation is indicated here. When we crank through that quadratic math, which we'll do in the module on binding kinetics, we see that SRL is equal to 0.5 times KD plus SRT plus LT minus the square root of KD squared plus SRT squared plus LT squared plus 2 KD SRT plus 2 KD LT minus 2 SRT LT. Right, so that's a bit of a mouthful to say, but it's pretty easy to enter it in a computer, and so we can use this equation in PRISM to analyze binding isotherms acquired under these circumstances. It can be quite useful for some purposes, of course, to consider fractional saturation. For conceptual analyses, fractional saturation, is sort of the natural coordinate system. It's just much easier to see things conceptually when we normalize and consider fractional saturation. So mathematically, that's pretty easy to do. We just divide through SRL divided by SRT. That would give us the fractional saturation, right? Dividing through by SRT gives us the fractional saturation of the receptor. These equations apply only to n equal 1. This quadratic, right, if n were equal to 2, we'd have a cubic equation. We get the quadratic equation when n is equal to 1. If n is equal to 1, right, let's contemplate that. When n is equal to 1, this is basically symmetrical in ligand receptor, right? If n is equal to 1, you have one ligand molecule, free ligand molecule, bounding to one free receptor molecule. These are entering this chemical equation symmetrically, right? When n equals to 1, also mathematically they're symmetrical, right? When n is equal to 1, a little bit messy. When n equals to 1, these are chemically, physically, and mathematically symmetrical. So this equation, if you look at it, right, SRT and LT are symmetrical. Every time we have an SRT term, right, SRT, LT, symmetrical. SRT, LT, symmetrical quadratic terms. SRT, LT, symmetrical, right? SRT, LT, symmetrical. This quadratic binding equation is symmetrical in SRT and LT, as it should be, because the problem is physically symmetrical. But in an actual experimental circumstance, we can do the experiment two ways. We can saturate the receptor with the ligand. What we've been doing mostly, what we've been focusing on in the PowerPoint is experiments conducted like that, where ligand is slowly titrated onto receptor and we saturate the receptor. In the laboratory, we can also do something called an inverse titration, where we titrate receptor onto ligand. In biophysics, it's often more convenient for various reasons to titrate receptor onto ligand, right? This curve is symmetrical in both of them. It doesn't matter. But when we go to fractional saturation, if we're looking at fractional saturation of a receptor, we have to divide through by SRT. If we're looking at fractional saturation of ligand, we have to divide through by LT. Okay? In either case, we start with this quadratic binding equation, but divide through to get the expression, to get a fractional saturation equation, to get an equation showing the fractional saturation of receptor as a function of total ligand, we have to divide through by SRT. We get this equation. To get an equation giving fractional saturation of ligand as a function of receptor, we have to divide through by LT. We get this equation. Now, these equations are no longer symmetrical because the experiment has not been done in a symmetrical way, right? The underlying equilibrium binding equation is symmetrical, but if we do the experiment differently, the experimental protocol breaks the symmetry of what is a physically symmetrical binding interaction, right? In this case, we're titrating on L total. We're looking at fractional saturation of receptor. We have to use this equation. Again, in many biophysical experiments, we'll do it the other way around. No problem. We just have to remember to divide the symmetrical quadratic binding equation by ligand rather than receptor. So these quadratic binding equations are all provided for you in files that you will find in Courseworks. And so you're never going to have to key them in. It is important to know where they come from. It is important to distinguish the fact that one of them, that when you're looking at fractional saturation of receptor as a function of ligand, you need a different equation than when you're looking at fractional saturation of ligand as a functional receptor, because even though the underlying equilibrium binding quadratic equation is symmetrical, the fractional saturation is, when you divide by SRT or alternatively LT, you break the symmetry mathematically and you have to use the right equation. Okay. So that's an important point, because the problem sets are going to, problem sets are going to need you to pay attention to that. Another important point, however, just to close this mammoth epic screencast, to bring the mammoth epic screencast to a close, in addition to knowing that you'll have to use one of these equations or the other, it is incredibly important to understand that ultimately what you're looking at in these quadratic equations are situations where there's a significant amount of receptor compared to KD, right? The quadratic equation is going to be applicable in situations where NSRT is at least similar to or greater than KD, right? So the quadratic equation is going to apply in situations where NSRT is similar to or equal to, is similar to or much greater than KD, right? If NSRT is much lower than KD, as we have with this black curve, right? If NSRT is much less than KD, the free and the total ligand are about going to be the same. There's an insignificant amount bound. If there's an insignificant amount bound, the shape of this curve just doesn't depend on the amount of receptor, right? If the receptor concentration is constant, if the receptor concentration is tiny, the amount of bound receptor, as we went through in the last slide, if the receptor concentration is tiny, the amount of bound ligand, right, with a tiny amount of receptor, you always have a tiny amount of bound ligand. The total ligand is always going to be the free plus the bound, but if bound is tiny, right, if you can ignore bound, the total is going to be dominated by the free. In that case, the shape of the curve just doesn't depend significantly on the total receptor concentration. If it doesn't depend significantly on the total receptor concentration, you can't do a mathematical analysis that's going to tell you anything about stoichiometry. Ultimately, you're inferring stoichiometry by, really what you're ultimately measuring is receptor concentration. If receptor concentration is tiny, right, you get stoichiometry by actually measuring the receptor concentration and normalizing it to your experimental estimate of receptor concentration. What you're actually measuring is real receptor concentration. If real receptor concentration is tiny, it does not change the shape of this curve. It's basically a free ligand curve. You should analyze it using the free ligand binding isotherm. On the other hand, as we bring in more and more, and again, there is a problem, these numbers are wrong, I apologize for that, I just noticed it while I was doing the screencast. I apologize if that's true, but when you bring in more and more free, right, the black curve is roughly equal to the free ligand. When you bring in more and more total receptor, you get more and more receptor bound as you're going through the titration. You get more and more of a displacement of the total curve from the free curve. The shape depends more and more on the amount of receptor. It depends in this regime, as we see here, it depends both on the KD and the SRT. You can use this single, right? You can use these mathematical equations on a single binding isotherm conducted under these conditions where SRT is roughly equal to KD. You can, in principle, use these equations to extract estimates of both SRT and KD from a single binding experiment, right? You can apply these equations to an experiment conducted on a single binding isotherm acquired under these conditions. You can apply these equations to estimate both the SRT and the KD. Now, what you'll see is if you do that on simulated data, you get back perfect values of SRT and KD because the shape does depend on both of those parameters. You'll also see that it doesn't take much noise in the experiment for those estimates to become very noisy. And so this is a complicated thing to do experimentally, so you should be aware of that. But most importantly, you should understand that to use that approach, at least in principle, you need the shape of the curve to depend both on SRT and KD. When you have a tiny amount of bound receptor, the shape of the curve is determined really entirely by the free ligand concentration. The bound ligand is you basically have if you have a tiny amount of receptor, you have a tiny amount of ligand bound. The shape just depends almost entirely on the free. On the other hand, if you have a huge amount of receptor, as we saw earlier, right, you have basically everything bound, and the shape does not depend significantly on the free. Under that circumstance, you're not going to get a good KD, but you can get a good SRT estimate and thereby stoichiometry estimate. In this regime, where KD is roughly equal to SRT, or KD over SRT is somewhere close to 1, the shape depends on both of these parameters. You can use this quadratic equation to extract them both simultaneously. So the equation simultaneously yields estimates of KD and S for experiments conducted on independent site receptors when SRT is about equal to KD. But the errors can be large without very high quality binding data that goes to full saturation. And of course, to do this at all, for this app to be applicable, to get both parameters out of it, you need to be in a regime where KD and S both strongly influence the shape of the observed binding curve. I should say that when SRT is very high, this equation still works, and you should still use this equation. This equation is still going to be able to fit the data. But if the shape of the curve does not depend significantly on KD, the estimate you're going to get of KD is going to be basically unreliable. And so hopefully as you go through the exercises and play with the data, you'll see exactly why that's the case. The previous slides explain to you physically why that's the case, right? If you don't have a significant amount of receptor bound, you can't really use an experiment to tell how much receptor is there. If you can't tell how much receptor is there, you can't estimate stoichiometry because you can't estimate SRT. If you don't have a significant amount of receptor free, the KD is given by their free receptor, right? If everything is bound, basically all you're going to be measuring, the primary thing you're going to be measuring is the receptor concentration. If all the ligand is bound and the receptor is just saturating it, you're measuring primarily receptor concentration. This equation still works. This is still the right equation to use to estimate SRT from a binding curve. But be cautious, because it will give you an estimate of KD, but it will give you a very inaccurate estimate of KD. The thing that ties this all together is an understanding more of nonlinear curve fitting math. We'll do that in the next course module in my undergraduate class. It is hard to hold this all together in your head at the same time. This screencast already has achieved Cecil B. DeMille length. Folks may be too young to know who Cecil B. DeMille is. He's someone who made movies that were 4 hours long. They were popular when I was a very young child. You may have seen some of these things. Anyway, this is a screencast of epic length. It ties together a lot of stuff. It covers probably the most important things I want you to understand about binding. I think probably the best thing for you to do if you're struggling with understanding some of this is to go off and work on the problem set. And then once you've worked on the problem set for a while, come back and look at the slides. The slides have all the key points. And listen to the screencast again if you have the patience for that. But the slides have all of the key points organized. And so the hope is that, the key things to understand about binding are pretty much encapsulated in this screencast. I apologize that it's so lengthy, but the lecture notes are compact, and hopefully as you try to solve the problems, you can go back to them and figure out, use the lecture notes as a resource to consolidate your understanding of what's going on here. This algebra is not particularly simple. It's not particularly complicated. I'll treat it explicitly in the module on binding kinetics. The algebra that we've done in this screencast is very simple. And so the concepts are not. So work on the problem set, think about the concepts, go back to the slides to look at the qualitative and conceptual points. If the math is confusing, ignore it. If the math is illuminating, look at it. The math is very simple. Try through working on solving the problems combined with referring to the lecture notes to pull all this together and see how far you get. And if you still have questions, you can come back to me and we can discuss it some more.